In this video, we're going to discuss about the SI unit. So, to start, what is the SI unit? Before we solve chemistry problems, we need a common language for measurement. Imagine doing an experiment where everyone uses different ruler, okay? So- and a different balance or even a different definition of a liter. Comparing results would be impossible. This is why science relies on a standardized system. By meaning standardized, there is a functioning system that we follow. So this system is called the International System of Units, or the SI unit. So if you wonder why it is called um, SI instead of IS, okay? Because this is international system, not system international, right? So this is due to its origin. This is actually from the French Revolution, and way back it is called Le Système International. And then yeah, it's basically the same thing, just switching the letter because of the English language. Okay, so SI units are the globally accepted standards used to measure physical quantities such as length, mass, time, temperature, amount of a substance, electric current, and luminous intensity, which we will discuss later on. So, by using SI units, scientists all over the world can communicate data clearly. Okay, and this is based on seven fundamental base units. Through this, scientists communicate data clearly, perform accurate calculations, and reproduce experiment reliably, which is an essential thing for reporting um, quantitative results. So this system is based on seven fundamental base units. So we must note this. Okay, these are easy to memorize and should be memorized if you want to know how such physical quantities are reported. So here we have seven here. So this will be the physical quantity, meaning this will be um, what we are measuring. Okay. And let's say this is the name of the unit and the abbreviation. Okay. Okay, the first thing would be for the physical quantity is the mass. Of course, the most common thing we measure. So we measure mass by a weighing scale. And what is the unit we usually use? It is the kilogram, right? This is the accepted unit as a unit, kilogram, okay? Not gram, not milligram, kilogram, with an abbreviation of small k and small g. Okay, remember that. For mass, we have kilogram. Next is for length. For measuring length, we follow the SI unit and word it as meter. Okay? Not kilometer, not millimeter, sorry. And with an abbreviation of M. Then followed by time, which is very, I think you know this. This is reported in seconds or second, and a symbol of S. Okay? Followed by temperature. So, what do you think is the as a unit for temperature? It's not Celsius, it's not Fahrenheit, it's Kelvin. Okay, this is what scientists use in reporting temperature. Okay, and that is abbreviated by a big K. Okay, then we have the amount of substance. This unit is very common, especially in chemistry. So, what is this? This is mole, okay? And its abbreviation is small letter MOL. Okay, so this represents the amount of substance. Followed by, so this one, I think some of the students don't know or not familiar yet to this. We have the electric current, which is reported in the SI unit for of ampere. Okay, and with an abbreviation of big letter A. Okay, note you must memorize this. Okay, the exam would just say mass and something would maybe would ask you what would be the SI unit for mass, and they would give you choices like kilogram, milligram, gram. Okay, but this is an easy part. Okay, let's see. Okay, the last one would be the luminous intensity or luminosity, something like that. Okay, and this is measured in units of candela. Okay, just think of a candle. It's luminous, right? Then with an abbreviation of small letter C, oops, small letter C and small letter D. Okay, so these are the seven fundamental base units that we follow um, from the international system of units. Okay, so for a brief introduction or a general overview of how SI unit was developed and came to this. And before SI units, measurements were not standardized. Okay, so different countries, even different cities, use their own units for land. So some countries measure units in stones, maybe in feet, but not standardized. Okay, this is a this the length of this stick is uh 5 or 6 stones. Then the other country or the other tribe would say 6 stones, and then they may use another stone, so it can be confusing. Okay, so some countries may use different units because they have different references of their measuring. Okay, so this caused confusion, of course. So confusion in what? Confusion in trade. There would be confusion in historical engineering, perhaps, um, confusion in scientific experiments. So in the late 18th century, okay, let's say this was the before SI unit. Okay, so this is before 18th century. Okay, before 18th century. Okay, this has confusion of measurement. Then this followed by the French Revolution. Okay, so something happened at the French Revolution that changes our ways or created a system that results to more proper reporting of measurement. Okay, so in French Revolution, this happened in the 18th century. So this may come up in your exam, especially in introductory chemistry. Okay, so in French Revolution, the metric system was introduced. So basically, metric system is a measurement based on powers of 10 and natural references. So we can say a decimal based international standard for measurement. Let's say we have meter. So it is in tens and natural references. So when we want to report it in uh, a lot, let's say we have 1,000 meter. Okay, this can be reported as and the same to 1 kilometer. So something like that. So this system was introduced at this time, and then along with this uh, power of 10 system. There is also natural references. By meaning natural references, we have physical object references. We have physical objects to refer to. Let's say 1 kilogram. Okay, this is true. Huh? So 1 kilogram was actually from a platinum iridium cylinder. Okay, platinum iridium cylinder. Platinum iridium cylinder. So this will be discussed later. But at this point, we are referencing our measure on some physical objects, natural references. So we have, for instance, this one. 1 kilogram is the weight of the platinum iridium cylinder in France. So that's like the standard kilogram back in the days. So after the 18th century, okay, so this happened in the 1875. So we have the Treaty of the Meter. So this is basically an international agreement which expand the metric system kind of, leading to the creation of international measurement organization. Then finally, we have the SI unit. SI unit, or as named before, it was called Le Système International. Okay, so it's from French, of course. So in English, it's SI unit. Okay, or International System of Unit, and was officially adopted, providing a unified system of base and derived units used in science today. So this is basically the brief history, or to discuss this further. Okay, this circle here. Okay, as I have mentioned before, the natural references such as this. So this is what I refer to, or what I was talking about, the platinum iridium cylinder. Okay, so this is true. This is found in France. I think is this is in a museum now. Okay, so this is equal to 1 kilogram. So when you say how much is 1 kilogram, they say that this is the perfect 1 kilogram. So that was before. But now you can just imagine that basing the measure of kilogram in this one metal cylinder, that would be a problem. So the problem was that this object could change, as it is a physical object which can get old and slightly over time due to surface contamination or material loss. It would not be a good reference. Okay, it might be a 1 kilogram before, but now it may be 0.9 kilogram something. Okay, so due to that, in 2019, okay, 2019, the scientists solved this problem. Okay, they created a redefinition of the SI unit's origin. Okay, so as you can see here at the outer circle, or at the outer layer of the circle, we have the seven fundamental units of the SI. We have the kilogram, the meter, second, ampere, Kelvin, mole, and candela. So, and what's the confusing part is what is this in the inner layer? Okay, we will discuss that. Okay, so in 2019, so I'm referring to this one. So this would be the easiest, but the concept remains the same for all of this. Okay, let's focus on kilogram. So kilogram was referred to this before, right? But in 2019, uh, they fix this value using the Planck's constant. So Planck's constant, okay, is a physical law. So rather than a physical object, this would be a better reference because it's a physical law. It is not gonna change, and this makes the unit stable, universal, and reproducible anywhere in the world. So this one in the eight is actually the Planck's constant. Okay, now the kilogram is originated from the Planck's constant. Okay, and so the same goes for this other units here. So in the outer layer, for instance, we have here um, meter. So meter is based on, so this was h. Okay, meter is based on the speed of light. Okay, speed of light does not change. So this is c. And second here is actually based on the transition frequency of cesium 133 atom. So this is a very specific, okay? That is the delta V here. And then we have amperes, and it is based on the electric charge, which is E, okay? And we have Kelvin, which is based on the Boltzmann constant, which is small letter k. And then we have the mole based on the sorry, Avogadro's number, which is n sub a. And we have candela, which is based on luminous efficacy, which is K sub CD. Okay, so this changes. In 2019, the reference of these units um, that came from physical references was changed to law origin, or now defined as um, units from physical law. So this made it authentic and non-changing, okay, with time, unlike this one, okay, the physical references. Okay, okay, now that our base units are clearly defined, the next challenge is the scale. So we can see here we have prefixes of units, okay? You might not be familiar here, iota, zeta, exa, but I think you're familiar around here. Kilo. We have centi, milli, okay? We can say kilogram, centimeter, millimeter, okay? So we'll discuss how this is used, okay? So in chemistry, we often deal with quantities that are either extremely large or extremely small. For example, atomic distances are incredibly tiny, okay? While solution volumes in the laboratory can be much larger. So writing all of these values using only base units, let's say we're just using saying meter to a size, and then we want we are measuring the radius of an atom. Okay, that would be around 0.0000000. So this would be very unnecessary. Okay, a lot of zero. So through using the prefixes of units, we can create a simpler way to report these such quantities. Okay, so to solve this, they have created SI prefixes, which represents power of 10. So you can see here, 10 to the power of something. Okay, so for instance, um, 1 centimeter is 10 to the negative 2 meter. Okay, and yeah, so that's it. So 1 milli would be equal to 10 to the negative 3. Okay, so for example, instead of writing 0.0000001, this would be what? 1, 2, 3, 4, 5, 6. Okay, so the value is the same when it is called as 1 mic okay, sorry, 1 micrometer. 1 micrometer, or in its symbol, 1 mu meter. Okay, so micrometer is 10 to the negative 6. Okay, so this is 1, 2, 3, 4, 5, 6. So the 1 is in the sixth from the decimal point. Okay, so this makes our reporting of quantities much easier to communicate, right? Instead of 0.000, you can just say it's picometer, nanometer, or something. Okay, so to practice this, I think we must solve some problems. But first, okay, you must remember that we really need to memorize this one. Okay, I know it's a lot, but it will be easy because these are just tens. Okay, we can say kilometer is 10 to the power of 3 meter. So something like that. This is easy to memorize when you just pick the most common units, okay, or the most common prefixes. Okay, so these are the most common prefixes that are usually used most often in the lab. So, okay, so from here, just here. These are like the most common thing you will encounter in the lab. Iota, zeta, I don't think so. So that is very rare, and zepto, yocto, rare as well. Femto is often used as well, but when you are in the lab, this one is usually used milli, micro, and nano. Eco sometimes. Centi, okay, we know centi is very common. Centimeter, especially in length. Okay. DC is also a use unit, but it is not often used because it's just like zero point 0.1. So some would just report 0.1 meter instead of 1 decimeter, right? Okay, we also have decameter, hectometer, and this one kilometer and megameter and gigameter are also often used in more macro scale measurement. So if you just memorize this one, you are good to go. Okay, these are the most common units used in exams as well. Okay, so to practice our comprehension or understanding in solving these prefixes, I have put some sample problems here, and let's solve this together. Okay, so these are just easy. Okay, we have three questions that are easy. So first is convert 3.50 kilometers to meters. So as you can see here, I didn't remove this because, okay, this is your first time. Maybe you haven't memorized this yet. Okay, but let's practice. Okay, so we will have 3.50 kilometers, and you want it to convert to meters. Okay, so let's start with the given. Of course, you have 3.50 kilometers. Okay, and 1 kilometer. Okay, so this is 1 kilo. How much is 1 kilo? It's 10 to the power of 3. So that would be what would mean that 1 kilometer would be 10 to the power of 3 meter. Okay, And now it's easy, right? We can just eliminate this km, and we're left with meter. So after eliminating kilometer from this, okay, dimensional analysis, we will have meter left as a unit. So 3.5 times 10 to the power of 3 meter, then we will have 3,500 meter. Okay, that's how prefixes work. Okay, you just multiply this. So very easy, right? You don't even need to do this dimensional analysis. Okay, let's see. For the example number two, so we have 425 milligrams convert to gram. Okay, let's see here, milligrams. So this would be milli. Okay, then what is the value? 10 to the negative 3. So we don't need to do this thing. We just need simply do 425 times 10 to the negative 3. Okay, negative 3. Then what is the answer? 420 times 25 times 10 to the negative 3. That would be 0.425 grams. Okay, very easy. Okay, this is from milligrams to grams. Next, okay, let's use the same logic. Okay, 0.0082 microliters to liter. Okay, so micro, let's see micro here. This is mu. Okay, mu is here as a micro. You also need to memorize this symbol. Okay, but micro, nano, milli, centi, kilo, very common. Okay, so okay, let's do it. 0.0082 microliter. Okay, micro is 10 to the negative 6. So simply multiply it by 10 to the negative 6. So 0.0082 times 10 to the negative 6. Okay, so this would be 8.2 times 10 to the negative 9 liter. So that is very small. So it's much better to use microliter in reporting instead of this one, 8.2 times 10 to the negative 9 liter. Okay, but that is the conversion of microliter to liter. Okay, so just use this, just multiply it directly, or you do this, but it will take some time. Okay, but you can just multiply it directly. Okay, just memorize this one, because of course in your quiz this will not be given. Okay, so let's try some. So for this one, convert 6.75 times 10 to the negative 3 gigajoules to kilojoules. So key here, gigajoules. Okay, and how much is gigajoules? 10 to the negative to the power of 9. So in how do we answer this? First by dimensional analysis. Okay, so we have 6.75 times 10 to the negative 3 gigajoules, right? And 1 gigajoules, how much? It's 10 to the power of 9 joules. But we want to convert it to kilojoules, not joules. So how much joules does 1 kilojoules have? So 1 kilojoules, let's find kilo. It's 10 to the power of 3. So 10 to the power of 3 joules. Okay. Now we can eliminate gigajoules and joules, and we are left with kilojoules. Now simply calculate using your calculator. Okay. 6.75 times 10 to the negative 3 times 10 to the power of 9 times 1 over 10 to the power of 3. Then you will get 6,750 kilojoules. Okay, so this is true dimensional analysis. So in this example, we must convert 2.40 nanosecond to millisecond. Okay, millisecond, not second. So let's start with 2.40 nanoseconds. So 2.40 nanoseconds, and if we look at here, what is the value of 1 nanosecond? That would be 10 to the negative 9. So simply times 10 to the negative 9, and that would be 2.40 times 10 to the negative 9 seconds. So from nanosecond, we have now second. Now we have the second, we want to convert this to millisecond. Okay, now we have the second, so we multiply it by 1 over the value. So over the value, what is the value of milli? 10 to the negative 3. So 1 over 10 to the negative 3. So that would be 2.40 times 10 to the negative 9 times 1 over 10 to the negative 3. This would be millisecond. Okay? So that would be 2.4 times 10, 2.40 times 10 to the negative 6 millisecond. So what is the concept here? So first, by converting the nanosecond to second, we simply multiply it. But by second to millisecond, we divide it. Okay? So in this case, I think dimensional analysis is much easier to understand, right? So through dimensional analysis, we can write it like this: 2.40 nanosecond times 1 nanosecond is 10 to the negative 9 seconds. So convert the second to millisecond. Now 10 to the negative 3 millisecond is actually 1 millisecond. Okay. Then you will just eliminate it and you're left with the millisecond unit. Okay. 2.4 times 10 to the negative 9 times 1 over 10 to the negative 3. So we are actually doing the same thing. And then we are left with 2.40 times 10 to the negative 6 milliseconds. Okay, so that's it. So thank you for watching. And if you want more examples of solving prefixes or conversions, please comment down below.